In this video, I'm going to go through everything that you need to know for bounds for GCSE Maths. So first off, we have to consider what actually is a bound. To investigate this, we're going to look at this inequality here, okay, which is saying that x is greater than 5, but is the same as or less than 12. So essentially, it's a number between 5 and 12, where we can be equal to 12, but we can't be equal to 5. And the question asks, what is the upper bound and what is the lower bound for x? Because there are two types of bounds you're going to be asked to find. So we first just need to figure out then, what do we mean by our upper bound and lower bound? Well, to investigate that further, I'm going to draw a number line, and we're going to represent x on this number line. Okay, so we've got the numbers 5 and 12. So I'm going to mark 5, I'm going to draw a circle there, and then I'm going to mark 12, I'm going to draw a circle over there as well. Now, given that we can be the same as or equal to 12, I'm going to shade this circle in, because that's what we do with inequalities when we could be equal to. Whereas given that the other inequality symbol is not the same as, I'm going to leave it unshaded. Then to represent all the values that x can take, I just need to draw a straight line joining up those two circles, and essentially x can be any number on that straight line. Now we have to consider what are the upper bound and lower bounds for x. Well, let's start with the upper bound. So informally, the upper bound is essentially the highest number you can be. Okay, so you might say in this case that 12 is the upper bound, and that is correct. Okay, we would say that 12 is the upper bound for x. So let's put more of a formal definition on upper bound. So the upper bound is the smallest number that cannot be exceeded. Now, if we consider the example I've gone through here with the 12, which we decided is our upper bound, okay, this number cannot be exceeded. Okay, if we go for 12.0001, that then falls outside of the range of my inequality. However, the fact that 12 can't be exceeded doesn't necessarily make it the upper bound. We have to establish there isn't a smaller number that also cannot be exceeded. So let's look at a number slightly smaller than 12. So for example, 11.999. This number could be exceeded because you could pop another 9 on the end, then another 9 like that, and another 9 like that. Okay, as long as we sort of got the 9s here, we can keep adding on another 9, and you're going to exceed the previous number. So as a result, the 12 would have to be the upper bound, as it's the smallest number we can't go greater than. Now let's consider lower bounds. Okay, so let's look at the 5 and see what's happening there. Because if I said that 5 was the lower bound for x, I suspect you'd question the fact that technically we can't be equal to 5, because our inequality up here was not the same as 1, and that's reflected by the unshaded circle on my diagram. However, actually, what we'll find is 5 is the lower bound for x. So let's just come up with our definition of the lower bound to explain why. So the lower bound would be, and it's essentially going to be sort of the opposite of what is written here, okay, it would be the largest number that you can't go below. So let's consider why this makes 5 the lower bound, despite the fact we can't actually be equal to 5 for the value of x. So let's take a value that's slightly bigger than 5, so for example 5.01. Could that be a lower bound? Well, the issue with that is, you can get a smaller number than 5.01 in this range here, because you could have 5.001. And then that can't be the lower bound, because you could have 5.0001, which is even smaller than that number. And we could just keep going on like that. We could keep popping another 0 in, and we're always going to get a number that's smaller than the one we're currently on. So therefore, a number of that format where we have 5 followed by a lot of zeros and then 1 cannot possibly be the lower bound. Okay, so our lower bound would have to be a number smaller than that, and the first number smaller than that would be 5. Now let's consider the other side of 5. So if we went smaller than 5, so for example 4.9, could that be the largest number that you can't go below? Well, no, it can't be, because you can get larger than that by adding another 9, so that 4.99, okay, which is a bigger number, okay, and then you could go 4.999 like that, and you could sort of just keep going. So none of these values that I'm writing out down here could possibly be the lower bound. The only number that's missing would be 5 itself. Therefore, we would say 5 is the lower bound, despite the fact we can't be equal to it. Okay, so you don't have to be equal to a number for it to be one of your two bounds. The final thing I'm going to say on these definitions is that technically, if you study maths at a higher level, an upper bound can be any number that is greater than the range you're considering. So any number that's greater than 12 could technically be called an upper bound. However, at GCSE, the expected definition you need to know for upper bound is for what we would call the least upper bound, which is the definition here, the idea that it must be the smallest number that could be classed as an upper bound. And we can say similar for the lower bound. Technically, the definition here is for the greatest lower bound, because any number that is smaller than the 5 could be technically classed as a lower bound. But for GCSE, we're going to go with these definitions that I've written here. Now let's have a go at finding the upper and lower bound for some rounded values. So let's look at our question. It says a table is measured in length as 150 centimeters, and that is correct to the nearest 10 centimeters. Then it asks what is the upper and lower bound for the length of the table, and we need to give our answer as an error interval, but let's focus on the upper and lower bound first. So essentially what's happened here is they've measured a table and they've got a result, then they've rounded it to the nearest 10 centimeters, so we would call this the degree of accuracy, and then the end result is 150 centimeters. What we need to figure out is the upper and lower bound, so essentially what is the highest and smallest value the actual length of the table could be before it was then rounded to 150. So let's consider the upper bound. You could start guessing numbers. So for example, 153 centimeters. Well, that rounds to 150 centimeters when rounded to the nearest 10. So if it's an upper bound, the idea is we can't go larger than this number. So let's think, is there a larger number that rounds to 150 when rounded to the nearest 10? Well, 154 rounds to 150. So therefore 153 cannot be the upper bound. And then we think 154, is there a larger number than that? Well, you could have 154.5 centimeters. That rounds to 150. So therefore the 154 can't be the upper bound. And you could keep going like that. But that's inefficient. We want to have a direct method of getting to the answer. So let's go through that. So I'm going to take this off. And what I'm going to do is draw a number line. And what we're going to do next is stick the number we're working with, so the 150 centimeters. We're going to stick this in the middle of my number line. So I'm just going to write 150 here. Then what we're going to do is consider our degree of accuracy. So that is the nearest 10 centimeters, so the nearest 10. So what I'm going to do is go to the 150, and I'm going to add 10 to this number, which is going to give me 160. And then I'm going to subtract 10 from 150, which gives me 140. And I'm picking 10 because it's my degree of accuracy. Now the 140 and the 160 are not my upper and lower bound. Okay, because that would imply any number between those two numbers rounds to 150 when rounded to the nearest 10, which is just not correct. Because you could take, for example, 158. If I was to round that to the nearest 10, that would round to 160. Okay, so clearly 160 is not the upper bound, and similar would happen for the 140, because if I picked, for example, 142, well, that rounds to 140, not 150. So actually what we'll find is that our upper and lower bound come from the midpoints of the numbers that I've got on my page. So if I calculate the midpoint between 150 and 160, and then calculate the midpoint between 140 and 150, that will give me my upper bound and my lower bound. So my midpoint over here would be 155. Okay, that is the central value between 150 and 160. Now, if you want a calculation for midpoint, all you do is take the two values, 150 and 160, add them together, and then divide by 2. And that would give you 155. That is a reliable calculation that will always work. And in the 155, that would be my upper bound. Now for the lower bound, that is the midpoint between 140 and 150. So that would be 145. So that would be my lower bound. Now what this means is any value between 145 and 155 round to 150 when rounded to the nearest 10. So let's pick a value. For example, if I was to pick this value here, which we'll say is 154, well, if I round this to the nearest 10, well, it's going to round to 150. And we can do similar on the other side. For example, if I was to pick 147, Well, if I round that to nearest 10, I would get 150 as well. So that makes sense. Now let's just consider the upper and lower bounds specifically. So if I was to take 145, does that round to 150 when rounded to nearest 10? Yes, it does. Okay, because the final digit here is a 5, we would round up. Whereas for the 155, that works a little bit differently, because if I was to round that to the nearest 10, we'd actually be rounding up to 160. Therefore, 155 would not be a valid value for rounding to 150 when rounded to the nearest 10, but we would still call it the upper bound because it's an upper limit. So we found our upper bound and our lower bound. Now let's consider the other part of the question, which says to give our answer as an error interval. Now when we're talking about an error interval, we're talking about inequalities. So I need to give my answer as an inequality. Now what I'm going to do is, given that this is considering length, I'm just going to assign a letter to the length. So let's call the length L. So I'm going to write L over here. And then in our inequality, we're going to write the bigger number to the right. So that's going to be my upper bound. 155 is going to go over here. And then my smaller number, which is the 145, our lower bound, that's going to go to the left over here. Then we just have to decide on inequality symbols. Well, our length has to be between the 145 and the 155. So therefore, the length is greater than 145, but it's going to be smaller than the 155. The final thing we just have to consider is whether these inequality symbols should be the same as or not. So we said 145 does round to 150 when rounded to nearest 10. Therefore, this would be a same as inequality. Whereas for the 155, that actually rounds to 160 when rounded to nearest 10. So this inequality symbol here would not be a same as. Now in my final answer, I should include units. So for the 155, I'm going to write centimetres. And then for my 145, I'm also going to write centimetres as well. Okay, and then this would be my complete answer for my error interval. So the idea is the error interval accounts for the fact that we can have the 145, hence why we have the same as inequality, whereas we can't have the 155, hence why we don't have a same as the inequality there. And what you'll find is when we do the error interval for a specific number rounded to a certain degree of accuracy, our lower bound will always be a same as inequality, whereas our upper bound will not be a same as inequality. So therefore, in future questions, we won't have to think so deeply about that. Let's have a look at another question. So here's our next question here. It says a distance is measured as 120 meters to the nearest 5 meters. So that's my degree of accuracy there. And we need to find the upper bound, the lower bound, and the error interval. So let's draw my number line. And the number we're working with is 120, so I'm going to put that in the middle. And then we're going to consider our degree of accuracy, which is the nearest 5 meters. So we're going to add that to 120 to get 125, and then subtract that from 120 to get 115. Now my upper and lower bound will be my midpoints. Okay, so my upper bound will be this value here. My lower bound is this value here. So my upper bound would be the middle between 120 and 125. So that's going to be 122.5. So that's my upper bound, so I'm going to write UB. For my lower bound, the midpoint between 115 and 120 would be 117.5. So that is my lower bound. And we should include units, so I'm going to put meters here and meters there as well. Now it does ask for an error interval, so let's write my inequality out. Now because it's a distance, I'm going to use the letter D to represent distance. So I'm going to write D. And then I'm going to write the bigger number, the upper bound to the right, so 122.5 meters. And then the smaller number, the lower bound to the left, 117.5 meters. Then we're going to put our inequality symbols in. So we said for the lower bound, it's going to be the same as or greater than, whereas for the upper bound, it's going to be smaller than, like that. And that would be my final answer. Let's have a look at another question. So we got m is equal to 15 kilograms to the nearest 100 grams. So that's my degree of accuracy. We need to find the upper bound and the lower bound for m. Now, one thing that people might struggle with on this question is the difference in units. Okay, because we've got grams, we've got kilograms. So what we can do is just convert the units. So for m, we're going to convert 15 kilograms into grams. So we need to times by 1,000. So we get 15,000 grams like that. Now the units are the same, so let's focus on our quantities in grams. So I'm going to draw my number line, and the 15,000 goes in the middle. Then given that our degree of accuracy is 100 grams, we're going to add 100, which gives me 15,100. And we're going to subtract 100 from 15,000, so we get 14,900. Now our upper and lower bound are our midpoints, so this value here and this value here. So my upper bound would be 15,050 grams. So I'm going to write UB. And then my lower bound would be 14,950 grams. So I'm going to write LB. And that's the final answer because we haven't been asked for an error interval on this question, so we could stop there. However, sometimes what you're required to do is to give your upper and lower bound in the other unit. So we got kilograms over there. So if you're writing it as kilograms, well, you need to divide by 1,000. So it would be 15.050 kilograms for our upper bound. And then for our lower bound, it would be 14.950 kilograms, like that. And the idea is any number between these two values here, round to 15,000 grams when rounded to the nearest 100 grams. Let's have a look at another question. So our question says h is equal to 6.5, and it says correct to 1 decimal place. That's our degree of accuracy. We need to find the error interval. So we're now dealing with decimals. So let's consider how we're going to do this. We're going to put the 6.5 in the center of my number line. And then we're going to identify our first decimal place, given that's our degree of accuracy. So our first decimal place is the 5. Then what I'm going to do is add 1 to this place value. So that would give me 6.6. And then I'm going to subtract 1 from the first decimal place. So we would get 6.4. Now they're not your upper and lower bound. Your upper and lower bound are your midpoints as usual. So the midpoint between 6.5 and 6.6 would be 6.55. So that would be my upper bound. Then my lower bound is the midpoint between the 6.4 and the 6.5. So that would be 6.45, like that. So that's my lower bound. Then we can write down my error interval. So the letter in this question is H. So I'm going to write H here. Then I'm going to write the upper bound to the right, so the 6.55. And then the lower bound to the left, so the 6.45. Then we just need to put in inequality symbols. So we said for the lower bound, h will be same as or greater than, whereas for the upper bound, it will just be smaller than, like that. And that is my complete error interval. Let's look at another question. So we got G, which is equal to 33.68, correct to 2 decimal places, our degree of accuracy. We need to find the error interval. So let's write our number line. And we're going to put G in the middle, which is the 33.68. And then we're going to identify the second decimal place because that's my degree of accuracy. So the second decimal place is the 8. So we're going to add 1 to that place value. So that gives me 33.69. And then we're going to subtract 1 from that place value to get 33.67. Then our midpoints will be our upper and lower bounds. So this is my upper bound. This is my lower bound. So my upper bound would be 33.685. That's the midpoint between this number here and this number here. Now let's do the midpoint between the other two numbers to get my lower bound. So that would be 33.675. So that's my lower bound. And then this here is my upper bound. So let's write out my error interval. So I'm going to write G, which is the letter that represents the number in this question. Write the bigger number to the right, so 33.685. The smaller number to the left, so the 33.675. And then my inequality symbols, as usual, will be same as or greater than for the lower bound, but then smaller than for the upper bound. Let's have a look at another question. So it says a number has been rounded to 2 significant figures. So that's my degree of accuracy, and we're now dealing with significant figures. And the result is 4,200. We need to find the error interval. So let's draw our number line, and we're going to put our number 4,200 in the middle. Now we're dealing with 2 significant figures. So let's identify where is the second significant figure. Well, the 4 is the first significant figure. So the 2 is going to be our second significant figure. So that's the one we're interested in. So what I'm now going to do is go to that place value, which is actually the hundreds in this case. And we're going to add 1 to that place value. So that's going to give me 4,300. And then we're going to subtract 1 from that place value, which gives me 4,100. Now our upper and lower bounds are going to be our midpoints. So the midpoint between 4,200 and 4,300 would be 4,250. So that's my upper bound. And then my lower bound is the midpoint between the 4,100 and the 4,200. So that's going to be 4,150. So that is my lower bound. Now we can write out our error interval. So we haven't been given a letter to represent this number, so I'm just going to call the number x. So I'm going to write x in the middle, the upper bound to the right, so 4,250, the lower bound to the left, so the 4,150. Then our inequality symbols would be the same as or greater than pointing to the x, and then the smaller than pointing to the x over there. So with significant figures, once you've identified which place value is that significant figure, it's much like the questions we've been doing previously. Let's have a look at another one involving significant figures. A number has been rounded to 3 significant figures, that's our degree of accuracy, and the result is once again 4,200. We need to find our error interval. So let's draw a number line, and we're going to put 4,200 in the middle. So let's identify our third significant figure. So the 4 would be our first, and the 2 would be our second. Now usually the trailing zeros are not considered significant. However, remember we've rounded a number to 4,200, so we have to consider where would the third significant figure be, and it would be the next place value along. Therefore, this is the one that we're interested in this question. Okay, so I'm just going to underline it here. And the idea is we're going to go to that place value, which is the tens, and we're going to add 1 to it, so we're going to get 4,210. And then we're going to subtract 1 from it. So if we're essentially subtracting 10 from 4,200, we're going to get 4,190. So then my upper and lower bound are my midpoints. So my upper bound would be 4,205. And then my lower bound would be 4,195. So then I can write out my error interval. This number hasn't been assigned a letter, so we're just going to call it x. So we're going to write x, my upper bound to the right, so 4,205, my lower bound to the left, so the 4,195, and we're going to put our inequality symbols in as usual, so same as or greater than pointing towards the x for the lower bound, and then a smaller than pointing to the x for the upper bound. Let's have a look at another question. So a number has been rounded to 3 significant figures, that's our degree of accuracy, and the result is 1.64. So we're considering decimals again, and we need to find our error interval. So let's draw a number line, and we're going to put the 1.64, the number we're dealing with, in the middle. Then the degree of accuracy is the third significant figure, so let's identify where that is. For decimals, the first significant figure is always the first non-zero number, okay, and then after that everything is significant, so this would be the second, and then the 4 would be the third significant figure. Therefore, that's the place value we're interested in on this question. So what I'm going to do is add 1 to that place value to get 1.65, and then subtract 1 from it to get 1.63. Then my upper and lower bound are my midpoints that I need to find. So my upper bound would be 1.645, and then my lower bound would be the midpoint between the 1.63 and the 1.64, so that is 1.635. So that is my lower bound. Then we can write out our error interval, so let's call our number x. So write x in the middle, upper bound to the right, and then lower bound to the left, so the 1.635. And then our inequality symbols are as usual, so the same as or greater than pointing to the x for the lower bound, and a smaller than pointing to the x for the upper bound. Let's have a look at another decimal. A number has been rounded to 1 significant figure, our degree of accuracy, and the result is 0.8. We need to find the error interval for the number. So I'm going to draw a number line, put the 0.8 in the middle. Now let's identify the first significant figure. So the 0 is not significant. Okay, in a decimal, the first significant figure is always your first non-zero number. So the 8 is the first significant figure, so that is the place value we're focusing on here. So we're going to add 1 to that place value to get 0.9, and we're going to subtract 1 from that place value to get 0.7. And then my midpoints are my upper and lower bound. So my upper bound would be 0.85, and then my lower bound would be 0.75. So then we can write out our error interval. Okay, we'll call our number x, x in the middle, upper bound to the right, 0.85, lower bound to the left, 0.75, and then the same as or greater pointing to the x for the lower bound, and a smaller than pointing to the x for the upper bound. Let's have a look at a scenario where this method that we're using here doesn't work. So it says a number is rounded to one significant figure, our degree of accuracy, and the result is 10. What is the upper bound and the lower bound? So let's draw a number line, and we're going to put 10 in the middle. Now the first significant figure would be the 1. So I'd go to that place value usually, and I'd add 1 to it to get 20. And I'd subtract 1 from it. Okay, and given it's the tens, we're essentially subtracting 10, so we're going to end up with 0. Then our upper and lower bound are usually our midpoints, so that would be an upper bound of 15. And then our lower bound, our midpoint down here, would be 5. So that's usually what we'd do. But let's just consider whether these answers make sense. Okay, so for example, if I was to take the number 6, which is between the 5 and the 15, okay, this theoretically should round to 10 when rounded to one significant figure. However, 6 is already rounded to one significant figure. If you round to one significant figure, you just get 6. So 5 being the lower bound doesn't make sense. Okay, so this method has failed. Okay, this has not got me the correct answer. And we could consider some decimals as well. If we take, for example, 7.4. If I was to round 7.4 to one significant figure, well, that would just be 7. Okay, that's not rounded to 10 to one significant figure. Therefore, the 5 as the lower bound does not make sense. Because 7.4 is clearly larger than 5 and still does not even round to the 10. Now let's just check the other side of things with the upper bound. If I was to take, for example, 13, if I was to round that to one significant figure, well, the first significant figure is the 1, the 3 is smaller than 5, so we would round down to 10. So that makes sense. So our upper bound of 15 seems okay. So this here is correct. The issue is our lower bound. So to figure out what our lower bound should be, because it shouldn't be 5, let's just start guessing. Okay, let's see how we do. So for example, if I was to take the number 9, if I was to round that to one significant figure, then I'd just get 9, because 1 is already rounded to one significant figure. So let's consider a number bigger than 9, so let's go 9.3. If we round that to one significant figure, well, 9 is the first significant figure, the 3 is below 5, so we're going to round down, and we're going to get 9 again. Okay, so we haven't got 10, so that doesn't make sense either. So let's go with 9.5. Well, if I round that to one significant figure, the 9 is the first significant figure, the 5 is 5 or above, so we're going to round up, and we would get 10. So it appears 9.5 is actually the first value for which we are going to round up till 10. So it appears that 9.5 should actually be our lower bound in this scenario. So if we were to consider our error interval, let's call our number x. So I'd write x in the middle, our upper bound, which was the 15 to the right, and our lower bound, which was the 9.5 to the left. Then we could put our inequality symbols in, so it'd be same as or greater towards the x, and smaller than towards the x. So this error interval looks different to all the ones we've had so far. So our answer here looks a little bit different to our previous error intervals that we've been dealing with so far. If I scroll back to the previous question, our initial number here was 0.8. Now if we look at my upper bound and my lower bound, these are symmetric about 0.8. They both have a difference of 0.05. Now if we go back another question, if we look at the number we're initially working with, the 1.64, well, our upper and lower bound are once again symmetric about that number. Okay, they are both 0.005 away from the 1.64. Now let's just consider one of our whole number answers. So our initial number in this question was 4,200. If we look at our lower bound and upper bound, both of those are 5 away from 4,200. So once again, it's symmetrical. Whereas if we look at the question we just did, where our method did not work, okay, you can see that our error interval is not symmetrical. Our initial number is 10, 9.5 is 0.5 away, whereas the 15 is 5 away. So in this scenario, we've got a very different answer. Now, why has this happened? Again, how can we figure out which other numbers this would occur for? Well, if we consider whole numbers, to the left of 10 and to the right of 10. What makes them different? Well, if we got 10, a whole number to the left is 9, a whole number to the right is 11. Well, you can see this is a 1-digit number, this is a 2-digit number. The fact that we changed the number of digits has caused this. So if we consider when is this going to happen again, well, it would happen once we reach 100. Because to the left of 100 we have 99, which is 2 digits, whereas after 100 we have 101, which is 3 digits. So do just be careful with numbers like 10, 100, 1000, and so on, where the number of digits change either side. Now let's have a look at truncation. So we're going to look at truncation, and just to begin with, we're just going to recap how truncation actually works. So we've got a number here, and we need to truncate to 1 decimal place. So what you need to go and do is identify the first decimal place, which is a 6, and simply you were just going to delete everything after that. Okay, so you're going to remove everything after that regardless of what digit comes next. So the answer to 1 decimal place would be 5.6. So this is easier than rounding, okay, because you don't have to consider the second decimal place. Let's look at part B. So part B says 3 decimal places. So the third decimal place would be the 8. So therefore we would rub out everything after that. So the 4 and the 2 are gone. So the final answer is 5.678, like that. And that's truncation. So let's now consider bounds. So it says find the error interval of x if x is 3.5 when truncated to 1 decimal place. So it's the result after the truncation. And we need to find the upper bound and the lower bound to be able to write our error interval. So what could have this number have been before the truncation? So our previous method was to draw a number line, write the 3.5 in the middle, and because we are dealing with 1 decimal place, I'd go to the first decimal place, which is the 5, and I'd add 1 to that place value to get 3.6, and subtract 1 from that place value to get 3.4. Then our upper and lower bounds were the midpoints. Okay, so this value here and this value here. So that would give me 3.55 and 3.45, like that. Now, if we consider whether this answer makes sense, well, if it was correct, any number between these two must truncate to 3.5 when truncated to 1 decimal place. So let's say we were to pick a number over here. Okay, so let's go with 3.46. Well, if I truncate that to 1 decimal place, the first decimal place is the 4, so we delete everything after that, so we get rid of the 6, so we're just left with 3.4. But it's clearly not truncated to the 3.5. Therefore, this answer cannot be correct. So what we're going to do is approach this in a bit of a different way. So I am just going to rub off what we've done here because this method is not going to work for these ones like it did for the rounding as usual. And initially, I'm just going to start guessing numbers. So what number does truncate to 3.5? Well, the number 3.54, that would truncate to 3.5 to 1 decimal place. Now, let's consider upper bound first. Can I beat 3.54? Can I get a higher number? Well, 3.58, that truncates to 3.5, so that's fine. Can I go higher? Well, 3.59 truncates to 3.5. Can I get higher than that? So that would be 3.61. Now, if we truncate that to 1 decimal place, we just get 3.6. So it seems we've gone too high. So if we go to, say, 3.6, well, that's just going to truncate to 3.6. So we need to go below 3.6. And the reason is, when we're truncating to 1 decimal place, we need our 1 decimal place to match our answer. Okay, so we need the 5 to be the first decimal place. So if I was looking for a bigger number than 3.59, so what we would need is our number to start, 3.5 something. Okay, and if we try and beat 3.59, well, I could write my 9 and then say a 1 or a 5, or even better, if we're trying to go higher, a 9, and then write another 9, and then write another 9. Okay, so it seems that 3.5 and then 9, 9, 9, 9, 9, 9, and so on would truncate to 3.5. Therefore, our upper bound is going to be equal to 3.6. Because even though this technically doesn't truncate to 3.5, as we saw here, this number is the upper limit, so it is the upper bound. Now let's consider my lower bound. Well, we said if it's going to truncate to 3.5, the number needs to start as 3.5 something. Now, the number 3.5 itself does truncate to 3.5. So therefore, we only want to go lower than this number. So if we're going lower, we'd then be at 3.499 and so on. But that's going to truncate to just 3.4. So that's not going to work. So therefore, 3.5 itself would be our lower bound. So for truncation, Your lower bound is going to be the number itself. The upper bound, to get that, you're going to have to go to your degree of accuracy, which is 1 decimal place, so the 5, and you're just going to add 1 to it, and then that's going to get you your upper bound down here. So that's going to be our method for how we're going to get the upper bound and lower bound for truncation. Now let's write out my error interval. So I'm going to put x in the middle because that is what the number is called in this question. We'll write our upper bound to the right, so the 3.6, lower bound to the left, so the 3.5, and then we just have to decide on inequality symbols. So we can be equal to 3.5, that's fine. We showed up here that does truncate to 3.5. Therefore, this would be a same as or greater than, pointing to the x, would have the same as in there. Whereas we said for the 3.6, which we demonstrated down here, we can't technically be equal to that. Okay, so it's just going to be a smaller than pointing to the x. And any value between the 3.5 and the 3.6 would truncate to 3.5 when truncated to 1 decimal place. So that's my final answer. Let's look at another one where we're going to try and get the answer a little bit quicker. So here's our question. A weight W measurement is truncated to 24.35 kilograms to 2 decimal places. That's my degree of accuracy. What is the error interval for W? So let's start with my upper bound. Well, we said for the upper bound, what we're going to do is go to our degree of accuracy, so the 2 decimal places, and figure out where is that second decimal place. Well, that's going to be the 5, and we're simply just going to add 1 to that place value. So we're going to get 24.36 kilograms. That's my upper bound. Then my lower bound, well, that's the easiest part. That is just going to be the number itself. Because if we go smaller than that number, our second decimal place is then going to be a 4. So therefore, the number is going to truncate down to 0.34 instead. So therefore, our lower bound is just going to be 24.35 kilograms. So we can write out my error interval. Our number is called W. Okay, our upper bound goes to the right, so 24.36 kilograms. Lower bound to the left, so 24.35 kilograms. And just like our rounding ones earlier, the same as or greater than is going to be pointing to the W there, whereas it's just going to be a smaller than for the upper bound pointing to the W. And that would be my final answer. Now let's consider bounds for calculations. So we're now going to consider bounds for addition calculations. So let's look at this scenario here. It says the possible values for x are 2, 5, and 8. So they're the only values I can pick for x. And it says the possible values for y are 20, 23, and 26. So they're the only values I can pick for y. Then it says what is the upper bound and lower bound of the calculation x plus y. So essentially what this is asking is if you picked a value for x out of the possible 3 we could select, and if you pick the value for y out of the possible 3 we could select, what is the highest answer we could get, which would be our upper bound, and what is the lowest answer we could get, which would be our lower bound? So let's start with our upper bound then. So I'm going to write upper bound of x plus y, just to indicate what I'm doing. And let's look at my numbers. So I need to pick a number for x and a number for y. Now, given that this is addition, if you want the largest answer out of an addition calculation, well, you want the numbers in the addition calculation to be as large as possible. Therefore, for my x, I want to use 8, which is the biggest possible value. And then for my y, I want to use 26, which is the biggest possible value. So we would have 8 plus 26, and that is equal to 34. So that would be our upper bound of the x plus y. Now let's just consider what we've done here. Okay, the 8 we said is the largest value for x. So in other words, that is the upper bound for x. And then the 26 was the largest value for y. So in other words, that is the upper bound for y. Therefore, if you want to do the upper bound of an addition calculation, you need to do upper bound plus upper bound. So as a generalization, the upper bound of x plus y is equal to the upper bound of x plus the upper bound of y, like that. Now let's consider our lower bound instead. Okay, so let's just think, how am I going to make my addition calculation as small as possible? Well, I'd want the two numbers being added together to be as small as possible. So what's the smallest value for x? Well, that's 2. So I'm going to write that in. And what's the smallest value for y? Well, that's 20. So I'm going to add that one. So our final answer would be 22. And if we look at what we've used, the 2 was the lowest value for x. So that is the lower bound for x. and the 20 is the lowest value for y. So that would be the lower bound for y. So as a generalization, the lower bound of an addition calculation is going to be equal to the lower bound of one number in the calculation plus the lower bound of the other number in the calculation. So now let's look at a different question where we're going to make use of what we've written out here. So here's our question. It says Hannah connects a car to a trailer. So I'm just going to draw a picture to visualize. I'm going to draw my car, which I'll label C, and then the trailer, assuming it's perfectly connected to the car, it should start straight away from there, and then I'm going to call that T. Now it says the car is 6.5 meters to the nearest 10 centimeters. So this is already telling me this is a bounds question because I've been given a value that's already been rounded to a degree of accuracy, which in this case is 10 centimeters. And then it says the trailer is 4.5 meters to the nearest 10 centimeters. So that has also been rounded. It says work out the error interval for the length of the car connected to the trailer. So to calculate the length of the car connected to the trailer, I need to do the length of the car added to the length of the trailer. So therefore, given that we've identified this as a bounds question, it's going to be a bounds addition question because we're going to be adding two quantities together. So what I need to start by doing is writing out the error intervals for the numbers given in the question. So the length of the car and then the length of the trailer. So let's start with the car. And what I know about this information is that there's different units. So I'm just going to convert our units. So for our car, okay, I'm going to convert the 6.5 meters into centimeters. So it's going to be 650 centimeters. And then we're doing the nearest 10 centimeters. So I'm going to draw my number line because this is rounding, it's not truncating. And I'm going to put the 650 in the middle. And then our degree of accuracy is 10. So we're going to add 10 to get 660, subtract 10 to get 640. And then we can write out my upper and lower bound. So my upper bound is going to be 655. And then my lower bound is going to be 645. So my error interval for my car, if we call my car C, the upper bound is 655, the lower bound is 645. Okay, and we can be the same as or greater than the 645 because we can be equal to it, but we can't be equal to the 655. So I'm just going to put a smaller than pointing towards the C. So that's the car done. Now let's do my trailer. Okay, so I'm going to write trailer over here. And once again, the units are different. So let's just convert the 4.5 meters to centimeters. So that would give me 450 centimeters. And once again, we're nearest 10. So the method's going to be the same. We're going to add 10 to get 460, subtract 10 to get 440. And then my upper and lower bound for the trailer is going to be my midpoints. So we're going to have 455 and 445 like that. So let's call my trailer T. And my lower bound is 445. My upper bound is 455. And then my inequality symbols will be the same as that for my car. So same as or greater than pointing to T, and then smaller than pointing to T. Now the one thing I did forget is my unit. So centimeters, 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 and then let's just squeeze these centimeters in next to the 645 like that. Now we've worked out the error intervals for each individual number. We now need to consider what we're actually asked to do to answer the question. So we need to work out the error interval for the length of the car connected to the trailer. So we said that's addition. So I need the upper bound for C plus T and then the lower bound for C plus T. So let's try and make use of what we've got here to answer the question. So to get our error interval, we're going to have to find our upper bound and lower bound. So let's start with my upper bound for my calculation. Okay, essentially we're trying to find the upper bound of C plus T. And the upper bound of C plus T is going to be equal to the upper bound of C plus the upper bound of T. Because that's what my formula here says. For addition, we do upper bound plus upper bound. So my upper bound for C is 655. And then my upper bound for T would be the 455. So I'm going to add those together. And then that's going to give me an answer of 1,110 centimeters, which we can convert to meters if you want. So I believe that's going to be 11.1 meters. Now let's do my lower bound instead. So for my lower bound, it is just the lower bound plus the lower bound. It's the two numbers I haven't used yet. Okay, the lower bound of C plus T is equal to the lower bound of C plus the lower bound of t. So the two numbers I'm going to be adding together this time will be the 645 and the 445. So I would be doing 645 plus 445, and then that's going to give me an answer of 1090 centimeters, which if we convert to meters would be 10.9 meters, like that. So now we can write out my error interval. So what I'm going to do is write c plus t in the middle, as that's what we're working out bounds for. My upper bound 11.1 will go to the right, and then my lower bound of 10.9 will go to the left. Now the final thing we just have to consider is, do we have to do same as inequalities or not? Because previously, for our individual numbers, if we have a look at what we've written up here, okay, we always had a same as at the bottom and then a not same as at the top. However, don't always assume that's going to be the case for calculations. So to figure out whether our inequalities are going to be same as or not, we just have to consider, where did these values actually come from? Okay, what numbers were added to get them? If we start with the 10.9, well, to get the 10.9, we added together the 645 and the 445. We're then going to have to consider whether we could have actually had those values for the length of the car and the trailer. So let's start with the 645, where if we look at the inequality for that, it is over here. And you can see we do have a same as inequality for the 645. Therefore, the car length could actually be equal to 645. Now let's consider the 445. Okay, and let's go to the inequality for that. So that appears over here. Now if we look once again, we've got a same as inequality with the 445. Therefore, the trailer length could be equal to 445. So we can actually have that value, and therefore we can actually have our lower bound of 10.9. So my inequality symbol would still be a same as or greater than, pointing to the c plus t. Now let's do a similar consideration for my upper bound. Okay, so that is the 11.1. So let's look at the numbers that created the 11.1. So we've got the 655 plus the 455. Let's start with the 655 and look at where that came from in my error intervals earlier on. Well, that came from over here, and you can see the inequality is not the same as. Therefore, the length of the car cannot be equal to 655. Therefore, 655 is not actually a length of the car, and that means we can't actually be equal to the 11.1. And we don't even have to consider the 455 because we know that we can't actually have the 655. Therefore, we're not going to have a same as inequality in my error interval. Okay, we're just going to have a smaller than pointing to the c plus t. So in this case, our inequalities have come out as the same as our error intervals for our individual numbers, but you'll see when we move on to other operations that this won't always happen. Now let's have a look at subtraction, where we're going to get that issue. So now we're going to consider bounds for subtraction calculations. So it says the possible values for x are 2, 5, and 8, and then the possible values for y are 20, 23, and 26. We need to figure out what is the upper and lower bound of the calculation y subtract x. So we're interested in subtraction here. The idea is I need to pick a value for y out of our three possible options, and a value of x out of our three possible options, and we want this subtraction calculation to be as big as possible for the upper bound and as small as possible for the lower bound. Let's start by considering the upper bound. So I'm going to write UB, and in my calculation here is y subtract x. I'll put that as the little subscript here, and it equals to, and we now need to select a value of y and a value of x that is going to give me the largest possible value of y subtract x. Now let's think of subtraction as finding the difference between two numbers. Essentially, I need to pick a value from the y numbers and a value from the x numbers such that the difference between the two numbers is as large as possible. So therefore, what you're going to want to do is for y, pick 26, and then for x, pick 2, because those are the two numbers that have the biggest difference. So the calculation we want to do is our value for y, 26, subtract our value for x, which is 2, and that is going to give us the biggest difference, which is 24. Now let's consider how we picked these numbers. The 26, that's the highest value of y, so therefore we pick the upper bound for y, and then the 2 is the lowest value for x, so therefore we pick the lower bound for x. So you can see there's a bit of mix and matching going on here. We didn't just pick the upper bound and the upper bound. Okay, it was a mix between upper bounds and lower bounds. So let's write out our generalization for subtraction. If you want the upper bound of y subtract x, then that is going to be equal to the upper bound for y, so the first value in your calculation, and then subtract the lower bound of the second value in the calculation, which is x. So that's how you figure out an upper bound for subtraction. Now let's consider lower bounds instead. So I'm going to write LB y subtract x. So thinking once again of subtraction as the difference between two numbers, we now want the difference to be as small as possible. So which value could you pick from y and which value could you pick from x such that the difference between the two is as small as possible? Well, you'd have to pick the 20 from y and the 8 from x, as they're the two values that is the closest together. So for y, we've got 20. For x, we've got 8, so we're going to subtract 8, and the answer comes out as 12. So that's our lower bound for our subtraction calculation. Now let's consider which values we picked. Well, for y, we picked the lowest value, so we picked the lower bound for y, for the first number in the calculation, and then for x, we picked the largest value. Okay, so in other words, we picked the upper bound of x. So therefore, if you want to figure out the lower bound of a subtraction calculation, you want to do the lower bound of the first number in the calculation, subtract the upper bound of the second number in the calculation. So once again, we're mix and matching. Now let's have a go at using these to calculate the upper and lower bound in some other scenarios. Let's have a look at this question here. So it says for the right angle triangle below, we've got A as 8.3 centimeters to the nearest millimeter. So that's already telling me this is a bounds question because the 8.3 is the result of rounding to the nearest millimeter. And then B is 6.1 centimeters, also to the nearest millimeter. We need to calculate the upper and lower bound for C, so that's confirmed this is a bounds question, and we need to give our answer as an error interval. Now let's have a look at the scenario we've got here, because we need to figure out which calculation we're going to do to figure out C. Well, we've got a right angle triangle, and C is a side length in the triangle. What do I know about a right angle triangle when it comes to its side lengths? Well, we can use Pythagoras' theorem. Okay, so C, that's our shorter side. So C squared is going to be equal to our hypotenuse A to the power of 2, subtract our other shorter side B, also to the power of 2 like that. So that's the calculation for C squared, but I want to find C, so we're going to have to square root both sides. So we would get C is equal to the square root of A squared subtract B squared like that. So what we've confirmed here is that this is going to be a subtraction calculation that we're interested in. Now, the fact there's a square root doesn't really change things. If you want a square root to be as large as possible, so your upper bound, we need the calculation under the square root to be as large as possible. And if we want the square root calculation to be as small as possible, then we want the calculation under the square root to be as small as possible, which is, of course, a subtraction calculation. So we're going to make use of these two rules we've written up here. Now, before we try and use those rules, we need to go to A and B and figure out their error intervals, okay? Figure out what is the upper and lower bound for each of those two values. So let's get started with A. So it says A is 8.3 centimeters, but we're working to the nearest millimeter. So I'm just going to convert the 8.3 centimeters to millimeters. So we'd have to times by 10. So we would get 83 millimeters to the nearest millimeter. Now we can have a go at finding our bounds. So we're going to draw a number line, put the 83 in the middle that we're working with. Now when it says nearest millimeter, that essentially means the nearest whole number, the nearest one, okay, because every millimeter is going to be a whole number. Okay, so the next millimeter would be 84, and then 85, and so on. So essentially rounding to the nearest whole number. Okay, so what I'm going to do is go to that 83, and we're going to add 1 to get 84, and we're going to subtract 1 to get 82. Of course, they're not my bounds. My bounds are my midpoints here and here. So for the lower bound, it's going to be 82.5 millimeters. And for my upper bound, it's going to be 83.5 millimeters. So let's write out my error interval. So I'm going to write A in the middle, upper bound to the right, so 83.5, lower bound to the left, so 82.5. And let's just stick the units on before I forget. Now we just have to figure out inequality symbols. So for a specific number, for the lower bound, it's always going to be a same as or greater than pointing to the A, but for the upper bound, it will just be a smaller than pointing to the A, like that. Now let's do B. So B was 6.1 centimeters to the nearest millimeter. So for B, if we convert to millimeters, it would be 61 millimeters if we times by 10. And of course, we're working to the nearest millimeter again. So then we can set up my number line, 61 in the middle. Now nearest millimeter meant nearest 1. So we're going to add 1 to get 62, subtract 1 to get 60. And then my upper and lower bound are, of course, my midpoints. So my upper bound is going to be 61.5. My lower bound is going to be 60.5. So then we can write out our error interval for B. So B is in the middle, upper bound to the right, lower bound to the left, and then the same as or greater than for the lower bound pointing to B, but a smaller than pointing to B for the upper bound. So that means we've got our two error intervals for our individual number. Now let's have a go at finding the upper and lower bound for C. So now let's consider our calculation for C, which is written here. Okay, because we need to find the upper and lower bound of this calculation in order to get our error interval. So I'm going to write UB upper bound for C, and that is going to be equal to the square root of, and then when we're dealing with upper bounds for subtraction, we're going to make use of this rule up here. So it's going to be the upper bound subtract the lower bound. Okay, so for A, it's going to be the upper bound, and don't forget we do have to square it, and then it's going to be subtract, and then for B, it's going to be the lower bound. So we're going to do the lower bound of B, and we just have to square it. So let's substitute our numbers in. So our upper bound for A would be the 83.5. So it's going to be 83.5 squared, subtract, and then my lower bound for B, so that is going to be this value here, 60.5. So it'd be 60.5 squared. And that calculation is going to give us our upper bound for C. So let's put it into the calculator. And we get 57.5, and it would be millimeters. You could convert to centimeters if you want, but I'm just going to leave it like that. Now let's have a go at the lower bound for C. So let's write LB and then C is equal to, and we know it's going to be a square root, but for our lower bound, we're going to make use of this rule here, which is lower bound subtract upper bound. So for the first number, we need the lower bound. So in our C calculation, our first number is A. So therefore, I need the lower bound of A, which I'm going to square, and I'm going to subtract the upper bound of my next number, which is B. So I'm going to do subtract upper bound of B to the power of 2 like that. So let's figure out which numbers we are going to use. So our lower bound of A would be the 82.5. So it's going to be the square root of, and it's going to be 82.5 squared, and then subtract. And then we need the upper bound for B. So that's going to be 61.5. So I'm going to subtract 61.5 squared. And then let's put that calculation into my calculator. And we would get 55.0 millimeters. Like that. So that means we calculated the upper and lower bound for C. The final thing that I need to do is give my answer as an error interval. So that's how I think about how we're going to do that. So what I'm going to start by doing is writing C in the middle, because that's the number I'm working with on this question. And we know my upper bound goes to the right, so the 57.5 will go over here. And make sure I put my units of millimeters in. And then my lower bound for C, the 55.0 millimeters, will go to the left. Like this. Now we have to consider inequality symbols, and this is where it becomes a bit complicated. So to figure out whether we're going to do same as inequalities or not, what I just have to consider is how did we get the 55.0? Which values did we use? Well, the values we used were the 82.5 and the 61.5. So we're just going to have to consider where those values came from. So let's start with the 82.5. Well, the 82.5 came from up here. And you can see for that, we used a same as inequality. So therefore, we can have 82.5. So it seems fine so far. But let's now consider the 61.5. Where did that come from? Well, that came from over here. And you can see the inequality is not a same as. Therefore, we cannot be equal to 61.5 for B. And as a result, we cannot be equal to the 55.0 we got out of the calculation we did using the 61.5. Therefore, my inequality symbol on my lower bound for C is not going to be a same as, which is a bit different to what we're used to. It's simply just going to be a greater than pointing to the C like that. Now let's consider our upper bound. So our upper bound was the 57.5, so let's just consider where that came from. So that's written over here. And let's look at which values we used to obtain that. Well, we used the 83.5 and we used the 60.5. So let's investigate whether we can actually be equal to those numbers. Let's start with the 83.5. Well, that was up here. And you can see the inequality symbol here is not a same as. Therefore, we cannot be equal to 83.5, and as a result, we cannot be equal to the 57.5, which we got by using the 83.5. Whether we can actually have the 60.5 is irrelevant if we can't have the 83.5. So my inequality symbol is not going to be a same as. So I am just going to put a smaller than pointing to the C. And in general for subtraction, this will be the case that neither inequality symbol will be the same as because of the way it works in terms of these rules up here. Because those upper bounds, we can't be equal to those. So as a result, both calculations we get for the upper bound and lower bound of our subtraction, we can't actually be equal to those either. Now let's have a look at multiplication. So we're now going to consider bounds for multiplication calculations. So it says the possible values for x are 2, 5, and 8. The possible values for y are 40, 80, and 120. And we need to figure out the upper bound and the lower bound of x, y, which means x multiplied by y. So if you pick one value for x out of the 2, 5, and 8, and one value for y out of the 40, 80, and 120, when we multiply them together, we want the highest value, which is going to be our upper bound, and the lowest value, which is going to be our lower bound. So let's start by considering our upper bound. So I'm just going to write upper bound and then xy and then equals to. And I need to pick one value for x and one value for y. That's going to get me the largest result for x multiplied by y. So logically, that's going to be the largest number for x, which would be 8, and the largest number for y, which is going to be 120. Because if I multiply them two together, so do 8 times 120, well, that's going to give me 960. And there's no way you're going to beat that value using a different pair of values of x and y, because the other values are smaller. Well, in terms of how we've selected which values we were going to use for x and y, the 8 was the largest value for x, so it's the upper bound for x. And then the 120 was the largest value for y, so that's the upper bound for y. So if you want the upper bound of a multiplication calculation, you need to do the upper bound of one number in the calculation multiplied by the upper bound of the other number in the calculation. Okay, so it's much like addition. If you want the upper bound, you need to do the upper bound and the upper bound. Now let's consider the lower bound instead. So our lower bound of xy, well, let's pick a value for x and a value for y that's going to make my multiplication as small as possible. Well, now we have to be looking at the smallest possible values of x and y. We'd want to use the 2 and the 40. Because if we do 2 times 40, we would get 80. And there's no way you're going to be able to get smaller than that by using a pair of values x and y. So let's just consider which values we picked. So for the 2, well, that was the smallest value of x. Okay, so we picked the lower bound for x. And then for the 40, well, that was the lowest value for y. So we picked the lower bound of y. So if you want the lower bound of a multiplication calculation, that is going to be equal to the lower bound of one number in the calculation multiplied by the lower bound of the other number in the calculation. So for lower bound, it's just going to be lower bound and lower bound, just like addition. So now let's have a go at making use of these two rules here to answer a question involving bounds and multiplication. So here's our question. It says a piece of silver has a volume of 590 centimeters cubed, and that is to the nearest centimeters cubed. So that's already a hint that this is a bounds question because that 590 is after rounding. Then it says if the density is 12 grams per centimeters cubed to two significant figures, so that's our degree of accuracy this time, we need to find the error interval for the mass of the silver. So let's just consider what calculation we need to do to find the mass. Well, this question's about density. Well, our formula for density is that density is equal to the mass divided by the volume. Now, I want to find the mass, so I need to multiply by the volume on both sides of my equation. So we would get density times volume is equal to mass. So that's my calculation to find mass. It's a multiplication calculation. Now what I'm going to do is just assign the letter D to density, V to volume, and M to mass just to help. Now what we have to start by doing is finding our error intervals for our individual numerical values given in the question. So that would be the 590 centimeters cubed and the 12 grams per centimeters cubed. So let's start with the 590, which is my volume. So for my volume, we have 590 centimeters cubed, and it's to the nearest centimeters cubed. Now, when it says nearest centimeters cubed, that is essentially the nearest whole number, okay? Because if you had 590.2, okay, if you round to the nearest centimeters cubed, it would be 590, which is essentially the nearest one. So let's draw my number line, and we're going to put the 590 in the middle, and our degree of accuracy is the nearest one. So we're going to add 1 to get 591, and subtract 1 to get 589. Then my upper and lower bound are my midpoints. So my upper bound would be 590.5. My lower bound would be 589.5. So let's write out my error interval. So I'm going to put V in the middle. My upper bound goes to the right, as usual. And let's just make sure we put our units on. So it'd be centimeters cubed. And then my lower bound to the left. And then my inequalities will be as usual for when we're doing the bounds for a specific value. So for V, it's going to be a same as or greater than pointing towards it for the lower bound. And then for V, it's going to be a smaller than pointing to it for the upper bound. So that's my error interval for V. We now have to do the same process for D, our density. So we're going to have to make use of this value 12, which is rounded to two significant figures. Okay, so we got D, which is 12 grams per centimeters cubed, and we got two significant figures. So let's draw my number line. So my number line is drawn, we'll put 12 in the middle. Now we need to identify the second significant figure. Okay, so that is going to be the 2, essentially the 1s. So we're going to add 1 to that place value to get 13, and subtract 1 to get 11. Then my upper and lower bound are of course my midpoints. So that's going to be 12.5 and 11.5. So now we can write out my error interval. I put D in the middle, and then to the right would have the 12.5, and my units would be grams per centimeters cubed. And then to the left would have 11.5 grams per centimeters cubed. And my inequality symbols will be the same as that for V, same as greater than pointing to the D there, and a smaller than pointing to the D there. Now let's have a go at using my two error intervals to find my error interval for the mass. So to find my error interval for the mass, we need to find the upper bound and lower bound. So let's start with the upper bound. So I'm going to write UB and then M. And the rule we're going to have to use is our one for the upper bound, which is written here. And to get my upper bound, I need to do my upper bound multiplied by my upper bound. So therefore, we need to do the upper bound of the density multiplied by the upper bound of the volume. So my upper bound for my density is going to be the 12.5. So I'm going to do 12.5 multiplied by my upper bound for the volume, which is the 590.5. And then I need to put that calculation into my calculator. And that gives me 7,381.3. And my units for mass are going to be grams, given that my density units are grams per centimeters cubed. So we got our upper bound for M. Now let's find my lower bound for the mass. So to do that, we're going to have to make use of this bottom rule here, which says the lower bound is equal to the lower bound multiplied by the lower bounds. So we need the lower bound for the density multiplied by the lower bound for the volume. So let's consider exactly which values I'm going to use. For my density, my lower bound was 11.5. And then for my volume, my lower bound was the 589.5. So if we put that calculation into the calculator, we get 6,779.3, and our units will be grams. So we've got our upper bound and lower bound for the mass. Let's write out our error interval. So I'm going to put M in the middle, and then my upper bound goes to the right. So that's going to be the 7,381.3 from over here. And we need grams. And then my lower bound to the left. So my lower bound is this value. So the 6,779.3 grams. Now we just need to decide on my inequality symbols and whether they're going to be same as ones or not. So let's consider my lower bound first, and let's think about where this came from. So it's written over here, and the calculation for it involved 11.5 and 589.5. So let's go and investigate whether we could actually have those values. So let's start with the 11.5. Well, that is over here. And what you'll notice is we have a same as inequality. Therefore, we can have the 11.5. Now, for the 589.5, that is over here. And once again, we have a same as inequality. Therefore, we can have the 589.5. And as a result, we can have the 6,779.3. So therefore, for my lower bound, it is going to be a same as inequality. Of course, the greater than will be pointing to the m. Now let's consider my upper bound. So my upper bound is the 7,381.3, which we can find over here. In terms of which numbers produced it, it's 12.5 and 590.5. So let's consider whether we could have actually had those values. So let's start with the 12.5. Well, we can find that over here. And as you can see, the inequality is not a same as. Therefore, we cannot have 12.5. And therefore we cannot actually have equal to 7,381.3 for the mass. So the inequality is not going to be a same as regardless of the 590.5. So it's just going to be a smaller than pointing towards the m like that. And that would be my final answer for my error interval. Now let's consider bounds for division. So we're now going to look at bounds for division calculations. So let's look at our scenario here. So the possible values for x are 2, 5 and 8. The possible values for y are 40, 80 and 120. And we need to know the upper bound and the lower bound of the calculation y over x. Or in other words, y divided by x. So essentially what we have to do is pick a value for y out of these three here. And then pick a value for x out of these three here to get the highest possible value, which is going to be my upper bound, and get the lowest possible value, which will be my lower bound. So let's start on my upper bound. So we've got to consider how we're going to get the highest value out of that calculation. So I'm going to write UB upper bound, and then I'm going to write y divided by x. Now we've got to think about division as trying to fit a number into another number. Okay, how many times can I get x into y? And for my upper bound, which I'm considering, I want to get x in as many times as possible into y. Therefore, what I want to happen is I want y to be as large as possible. So that would have to be 120. So we're going to write equals to, and I'm going to write 120 over. And then if we want to get x in as many times as possible, then I want x to be as small as possible. So therefore, I want the x to be 2, which is the smallest value for x. So we would do 120 divided by 2, which would give me 60. And it's not possible to get a larger value out of that calculation using the possible options for x and y that we had available to us. Now let's just consider which numbers I selected to do this. So the 120 we said was the largest value for y. So that's the upper bound for y. So we want the upper bound in my numerator. And then the 2 was the smallest value for x. So in other words, that was the lower bound for x. So therefore, we want the smallest possible value in my denominator. So let's write out a generalization. If we want the upper bound of a division calculation where we're doing y divided by x, then I want to do my upper bound of y divided by my lower bound of x. So to get my upper bound, I need to do upper bound divided by lower bound. So there's a bit of mix and matching, a bit like subtraction. Now let's consider the lower bound of our division calculation. And let's think about how we can get the smallest value out of this fraction. So to do that, we have to consider the fact that division, as I said, was fitting one number into another number. So if we want this calculation to get the smallest possible value, then I want y to be as small as possible this time, so I can fit the minimum number of x's into there. So we'd be using the 40. And then for my value for x, well, I want to get the fewest amount of x into there as possible, so we're going to use the largest value for x. So we're going to divide by 8, so our answer would come out as 5. Now let's just think carefully about which values we picked here. So 8 was the largest value for x, so that is the upper bound of x. Whereas the 40 was the smallest value for y. So that is the lower bound for y. So let's write out our generalization. If we want the lower bound of a division calculation, then we want to do the lower bound of the numerator divided by the upper bound of the denominator. So to get our lower bound, we're doing a lower bound divided by an upper bound. So once again, we're doing a bit of mix and matching, and this sort of matches up with our subtraction scenario. So let's have a look at a question where we're going to put these two rules to use. So here's the question. It says the average fuel consumption, which they're calling C, of a car in kilometers per litre is given by this formula here. And you can see that C is equal to D divided by F. So we have a division calculation for C. And it says that D is the distance travelled in kilometers and F is the fuel used in litres. Then they tell us that D is equal to 163, correct to three significant figures, and then F is equal to 45.3, correct to three significant figures. So both those values for D and F come after some rounding, so this is a hint that this is a bounds question, and our degree of accuracy in both cases is three significant figures. Then we are asked to work out the error interval for C. And remember, C is this division calculation over here, which is D divided by F. So we're going to end up making use of these rules over here eventually, because we need to find the upper bound and the lower bound for C to be able to write my error interval. But to get things started, we first need to consider the error intervals for our individual numbers, D and F. So let's start the process with D. So we got D is 163 and it's correct to three significant figures. Okay, that's my degree of accuracy. So for D, I'm going to draw my number line, put 163 in the middle, and then we have to identify the third significant figure. So that would be the 3, okay, the ones. So we're going to add 1 to that place value to get 164 and subtract 1 to get 162. Then my upper bound and my lower bound are of course my midpoints. So the upper bound is 163.5. My lower bound would be 162.5. And D is measured in kilometers, so these will both be kilometer values. Now let's write our error interval for D. So I put D in the middle, upper bound to the right, and then my lower bound to the left. And then my inequality symbols for a specific number are always going to be same as greater than for the lower bound pointing to the D, and then a smaller than pointing to the D for the upper bound. So that's my error interval for D done. We now have to move on to F. So F is 45.3, also correct to three significant figures. So I'm going to put 45.3 in the middle of my number line, and the third significant figure is going to be the 3. So we're going to add 1 to that place value to get 45.4, and then subtract 1 from that place value to get 45.2. Then my upper and lower bound are my midpoints. So my upper bound is going to be 45.35, and then my lower bound is going to be 45.25. And my units this time are going to be litres. So it'd be 45.35 litres and 45.25 litres. So now we can write out my error interval. So this is for F. So I'm going to stick F in the middle, upper bound to the right, lower bound to the left, and then my inequality symbols will be the same as those for D. So let's put those in. And then we've got our error interval for F. Now let's have a go at using these error intervals to find the error interval for C. So now let's try and figure out my error interval for C, and we're going to have to use this calculation up here, D divided by F. So let's start with my upper bound for C. Well, then we're going to have to make use of this rule up here, which says the upper bound is going to be equal to the upper bound divided by the lower bound. Okay, so for my numerator, we're going to use the upper bound, and that's of D, my numerator. And then for my denominator, it's going to be the lower bound, which is then the value F. So I'm going to write an F here. So now let's decide exactly which values we're going to use here. So we need the upper bound of D. So that's going to be the 163.5. And then we need the lower bound of F. So that's going to be the 45.25. And then we have to put that calculation into our calculator. And that gives me 3.61. And the unit in the question is kilometers per litre, given that the distance is in kilometers and the fuel is in litres. So I'd write kilometers and then per litre like that. Now let's consider my lower bound instead. So I'm going to write lower bound for C is equal to, and this time we're going to make use of this bottom rule here, which says the lower bound is equal to the lower bound divided by the upper bound. So for my numerator, I need the lower bound, which is of the value D. And in my denominator, I need the upper bound, which is for my value of F. So now let's pick the specific values we're going to use. So I need the lower bound of D, so that's 162.5. And then I need the upper bound of F, which is the 45.35. And then we're going to put that calculation into the calculator. And I get 3.58 kilometers per litre. So we can now have a go at writing out our error interval for C because we've got the upper bound and lower bound. So I'm going to write C, and then my upper bound to the right, so that's the 3.61 kilometers per litre. And then the lower bound to the left, which is the 3.58 kilometers per litre. Then we have to decide on my inequality symbols and whether they're going to be same as ones or not. So to do that, we have to go back to our upper bound and lower bound and consider how we got those values. So let's start with my lower bound of 3.58. So that is over here. And let's consider which values we use to obtain that. So we used 162.5 and the 45.35. So let's consider whether we can actually be equal to those values. So let's start with the 162.5. So where did that come from? Well, that came from over here. And as you can see, our inequality symbol is a same as one. Therefore, we can be equal to 162.5. Now let's consider my denominator, which is the 45.35. So let's think about where that came from. Well, that came from over here. And you can see our inequality symbol is not a same as one. Therefore, we cannot be equal to 45.35. And as a result, we cannot be equal to the 3.58 because that comes from a calculation involving the 45.35 we can't be equal to. So therefore, my inequality symbol for my lower bound is not going to be a same as one. So once again, this is mirroring addition. Now let's consider my upper bound instead. So my upper bound value was the 3.61, which is over here. And in terms of where we got that from, well, we used 163.5 and 45.25. So let's consider where those values came from. So the 163.5, well, that came from over here. And as you can see, the inequality symbol here is not a same as one. Therefore, we can't be equal to the 163.5. So as a result, we can't be equal to the 3.61, which comes from a calculation involving that 163.5. So therefore, we can't be equal to our upper bound. So the inequality symbol for our upper bound will also not be a same as one. So once again, this is match subtraction. And the reason this essentially ends up happening is because for our individual numbers, we can never be equal to our upper bounds. And you can see both of our rules over here involve the upper bound in the calculation. So therefore, logically, we're not going to be ever equal to our two bounds. So therefore, this down here would be our final answer to the question. Now let's have a look at some questions which involve a mix of operations. So we're now going to look at a question involving a mix of operations. So we got given that x is equal to p multiplied by q subtract r. So we got multiplication in here, but we've also got subtraction. So we got two different operations. And then we're told the values for p, q, and r, and they're all correct to two significant figures. So they're all the result of rounding. So that's the hint that it's the bounds question. We need to work out the upper and lower bound for the value of x, and we need to write our answer as an error interval. So given that we're dealing with both multiplication and subtraction, that means we're going to have to consider our rules for both multiplication and subtraction. So I've got those rules written here on the side, which are going to come into use later on. However, the first thing we're going to have to do is obtain the error intervals for P, Q, and R. Now the good news, they've all been rounded to two significant figures, and all the numbers are two-digit numbers. So therefore, the error interval should all take a similar format. So I should only have to do the error interval for one of these. So let's do it for P. So P is equal to 42. So what I'm going to do is put 42 in the middle of my number line. And it's two significant figures. So the second significant figure would be the 2. So we're going to add 1 to that place value to get 43 and subtract 1 to get 41. Then my bounds are going to be my midpoints. So it's going to be 42.5 for my upper bound and 41.5 for my lower bound. Now let's write out my error interval. So I'm going to put P in the middle, 42.5 to the right, 41.5 to the left. Let's put our inequality symbols in. So we know at this point that for a specific number, it's going to be the same as or greater than pointing to the P for the lower bound, where it's going to be a smaller than pointing to the P for the upper bound. So that's my error interval for P. However, because the other numbers are also 2 digits and have also been rounded to 2 significant figures, we can pretty quickly write out the error interval for Q and R. So for Q, which is 24, we'd be putting Q in the middle. And you can see for P, the 42.5 and the 41.5 have a difference of 0.5 with the 42. So we should get the same format for the Q. The Q is 24, so we're going to have plus 0.5, which is 24.5, and subtract 0.5, which is going to be 23.5, like that. And we'd have the same inequality symbols. So you can see we're just adding and subtracting 0.5 in order to get my upper and lower bound in this case. But let's do R. So R is 14. So I'm going to write R in the middle. Then 14 plus 0.5 is 14.5. And then we'll put our inequality symbol in. And then 14 subtract 0.5 is 13.5. And we'll put our inequality symbol in. So we now have our 3 error intervals. We now just need to make use of them in order to get the error interval for x. So let's start with the upper bound of x. So let's just remind ourselves of the calculation that we've got here. So it's P multiplied by Q subtract R. So multiplication is the overarching calculation that we're doing here. Okay, it's the P multiplied by the Q subtract R. However, within that calculation, we have a subtraction in those brackets there. So we're considering both rules. However, let's just consider the multiplication first, as that involves the entire calculation. So let's say we wanted the upper bound for multiplication. Well, that is going to be the upper bound multiplied by the upper bound. Okay, so I need the upper bound of P, and then that's multiplied by the upper bound of the other value in my calculation, which is the Q subtract R inside my brackets. Then what we're going to have to do is break down the upper bound of Q subtract R even further, given it's a subtraction calculation. So I would have the upper bound of P, which I'm not going to change, and then multiplied by, and I'm going to put it in brackets, okay, because it's going to be subtraction that we're dealing with here. And if we consider our rule for the upper bound of subtraction, well, that is going to be this one here. And that is our upper bound subtract our lower bound. So therefore, I need the upper bound of the first value in the calculation, which is Q. And we're going to subtract the lower bound of the second value in the calculation, which is R. So now we've got our upper bound calculation for x fully set up. So let's have a go at picking the numbers I need to use. So we're starting with the upper bound of P, which is going to be the 42.5. And then multiplied by, and then we've got the upper bound of Q next. So the upper bound of Q is going to be the 24.5. And then we got our subtract, and then we need the lower bound of R. So the lower bound of R is going to be the 13.5. So that is the calculation I need to put into the calculator. And we get 467.5. So that is my upper bound for x. Now let's consider my lower bound for x. So first off, let's consider the overarching calculation, which is a multiplication calculation. So we need the lower bound of multiplication, which is the lower bound times the lower bound. Okay, so I need the lower bound of P multiplied by the lower bound of the Q subtract R, which is in the brackets. But then what we're going to do is break up this lower bound of our subtraction even further. So we get equals to the lower bound of P multiplied by, then in brackets, because it's going to be multiple terms. And now let's consider our subtraction. So our lower bound for subtraction is our lower bound subtract our upper bound. So it's the lower bound of the first value Q, subtract the upper bound of the second value R, like that. Now let's go and pick which specific values we're going to use. So the lower bound of P, that would be the 41.5. Then multiplied by, and we're now doing the lower bound of Q. So the lower bound of Q is going to be the 23.5. And then we got subtract. And then we require the upper bound for R. Okay, so the upper bound for R is 14.5. So I'm going to put that in. And then we just have to put this calculation into the calculator. And we get 373.5. And that's our lower bound for X. Now we can write out my error interval for X. So X goes in the middle. Upper bound to the right, so 467.5. Lower bound to the left, so the 373.5. Now we just need to decide whether the inequality symbols need to be the same as or not. Now hopefully you've realised through the other examples we went through, if the upper bound is involved in our calculation, then we can't be equal to the result, because for the original numbers, we can't be equal to our upper bounds, because if you look at the inequality symbols for all our original numbers, for the upper bound, they're not same as. Now if we look back at our calculations for the 373.5 and the 467.5, you'll notice that the upper bound is involved in both of those calculations because we had subtraction involved. Therefore, neither of our inequality symbols are going to be same as. Okay, we just have a greater than pointing to the x and then just a smaller than pointing to the x like that. And that would be my final answer for my error interval. Now let's have a look at a different calculation involving these numbers p, q, and r. So here's our next question involving p, q, and r. We're asked what is the error interval for y, and we've got the calculation of y written here. So the p, q, and r are the same values that we were using, so I've got the error intervals for all of them written here. Now let's just investigate this calculation and see what operations we've got going on. So we've got a fraction, so that represents division, so we're considering division. Now it appears we have some multiplication between the 5 and the brackets. However, the 5 is not a value we've got after rounding. The 5 is just 5. We don't have to consider an error interval for that. So therefore, we don't really need to consider our rules when it comes to the 5 multiplied by the q plus r. We just have to consider the calculation inside the brackets, which does involve two numbers we have error intervals for, okay, which is an addition calculation. So for this question, we're considering addition and division. So I've got my rules for addition and division written here. So let's start with my upper bound of y. And the overarching calculation is the division. So we're going to consider the division first. So if I want my upper bound for division, okay, that is going to be my upper bound divided by my lower bound. Okay, so therefore, I require the upper bound of the numerator, which is the 5 multiplied by q plus r. And then I need that to be divided by my lower bound for my denominator, which is of p, like that. Now, given that the numerator involves an addition calculation, we're going to break that down further. Now, once I've got my addition calculation, I'm going to multiply by 5. That's always going to be there. So I'm going to start by writing 5, then open brackets. Okay, and we want the upper bound for addition here. So the upper bound for addition is always equal to the upper bound plus the upper bound. So we need to do the upper bound of q plus the upper bound of r like that. Okay, so that's going to be my numerator. Then my denominator is still going to be the lower bound of p. So let's go and select the specific values I'm going to use. So it's going to be 5, open brackets. Then we need the upper bound of q. So the upper bound of q is 24.5. Then plus, and then we need the upper bound for r. So the upper bound for r is the 14.5. And then we need the lower bound for p, our denominator here. So if we look for a lower bound for p, that is written up here. That's the one I want. So it's the 41.5. And then we just have to put this calculation into the calculator. And then the answer comes out as 4.70. So that's the upper bound for y. Now let's consider the lower bound for y. And maybe something you've noticed through the examples I've been doing is that essentially we're going to do the opposite for the lower bound. Okay, if we take this formula here we use for the upper bound, we're essentially going to switch all the upper bounds out for lower bounds and all the lower bounds out for upper bounds. So the idea is once you've done, say, the upper bound, doing the lower bound should be fairly swift. Okay, because we're going to want 5 lots of, and it's going to be the lower bound of q this time, plus the lower bound of r. And then for my denominator, it was the lower bound of p before, so it's going to be the upper bound of p now. So let's pick our values that we are going to use, and they're essentially going to be the 3 values we haven't used yet. So it's going to be 5 lots of, and then our lower bound for Q was the value 23.5. Then plus our lower bound for R, which was the value 13.5. And then we need our upper bound for P, which is the value 42.5. And then if we put that calculation into my calculator, we should get the lower bound for Y. And we get 4.35. Then we can write out our error interval for Y. So we put Y in the middle. The upper bound, which is 4.70, would go to the right. The lower bound, which is 4.35, would go to the left. And then we just need to decide if our inequality symbols are same as or not. Now we said if the upper bound of a specific value was involved in the calculation, then we can't be equal to the result of the calculation. So let's check that for the 4.35. Okay, if we look over here, you'll see that the upper bound was used in the denominator, therefore we can't be equal to the 4.35. So we'd have a greater than pointing to the Y, but not a same as. Now let's do the same check for the 4.70, our upper bound for Y. So that's over here, and you'll see the upper bounds were used up here in the numerator. Therefore, we cannot be equal to the 4.70, the result. So it'd be a smaller than pointing to the Y, and once again, not a same as. So that would be my final answer for my error interval of Y, and hopefully that example there has given you some advice on how to approach things a little bit quicker. So we're now going to look at a contextual question where maybe it's not so clear what we need to find in terms of whether we need upper bounds or lower bounds. So it says Bob is making lemonade for his party, and it says he has 34 guests attending. Then it says he makes 9 litres of lemonade, and that's correct to the nearest litre. So that's a hint this is a bounds question, because that 9 is after rounding to the nearest litre. Then it says he serves the lemonade in 250 milliliter portions, and that is correct to the nearest 10 milliliter. So once again, that's a value after rounding. Then it says, can he be sure that he has made enough lemonade to serve everyone 1 portion? And I must show my working. Now we've identified this as a bounds question based off these 2 lines here. So even if you don't understand how you're going to answer the question, the best thing to do to get started is to work out the error interval for any rounded values. So we need to do that for the 9 litres and the 250 milliliters. So let's get started with that before we consider how we're actually going to make use of those bounds to answer the question. So let's start with the 9 litres, which is the amount of lemonade or the volume of lemonade. So we're going to start by drawing our number line, and we're going to put 9 in the middle. Now it says to the nearest litre is the degree of accuracy, so essentially that's to the nearest whole number. Okay, so we're going to add 1 to the 9 to get 10, and subtract 1 to get 8. So our bounds are our midpoints here and here. So our upper bound is going to be 9.5 litres. Our lower bound is going to be 8.5 litres, like that. Okay, then we can write out our error interval. So what I'm going to say is, because the letter hasn't been assigned to this value, I'm just going to call it V and an L to indicate volume of lemonade. Okay, then my upper bound, 9.5, goes to the right. And then my lower bound, 8.5, goes to the left. And as usual, our inequality symbols will be a same as or greater than pointing to the middle from the lower bound, and then a smaller than pointing to the middle from the upper bound. So that's my error interval for the volume of lemonade. So now let's consider the other rounded value given in the question. So that would be the 250 milliliter portions. Okay, so we're now going to consider the volume of portions. And in our number line, we're going to put a 250 in the middle. And this time we're working to the nearest 10 milliliters, so the nearest 10. So we're going to add 10 to get 260, and we're going to subtract 10 to get 240. So then our upper and lower bound are our midpoints, so here and here. So our upper bound would be 255 milliliters, and then our lower bound is 245 milliliters, like that. So let's write our error interval, and once again, these numbers haven't been assigned a specific letter, so I'm going to call it V, the volume, but this time it's the volume of a portion, like that. So I write VP. When our upper bound 255 milliliters goes over here, when the lower bound 245 milliliters goes over here, and we'd have the same inequality symbols as for our other error interval, like this. Okay, so we got the error interval for the volume of the portion. Now let's have a think as to how we're going to use these error intervals to actually answer the question. Right, so what we've established so far is that the total volume of lemonade that Bob has made is somewhere between 9.5 litres and 8.5 litres. And then the portions that he's going to serve are somewhere between 255 millilitres and 245 millilitres. Now, I don't know what I'm going to do with these values yet, but the one thing I don't like about them is the fact that they have different units. So what I'm going to do is convert my litres into millilitres so they match. So to do that, we have to multiply it by 1,000 because there's 1,000 millilitres in a litre. So the 9.5 would become 9,500 millilitres, and the 8.5 would become 8,500 millilitres, like that. Okay, so I've got my error interval in terms of millilitres now as well. Now let's consider what calculations I'm actually going to have to do here. So let's just imagine for a second this wasn't a bounds question and we didn't have the nearest 10 millilitres part and the nearest litre part. Okay, so he had 34 guests. He's got 9 litres of lemonade and he's going to serve it in portion sizes of 250 millilitres. We need to be sure that he's made enough lemonade to serve everyone one portion. So how would we approach the question? Well, we'd want to figure out if he's giving out 250 milliliter portions to 34 people, well, how much lemonade does he need to give out? Well, he needs to do 34 multiplied by 250. Okay, because that's going to tell him how much lemonade he needs to give out. So putting that into the calculator, we would get 8,500 milliliters. Then what we'd do is we'd compare this value here with how much lemonade he's made, because 8,500 is how much he needs to give out. Well, how much he's actually made is 9 litres. So 9 litres is equal to 9,000 millilitres, and that is greater than 8,500 millilitres. So therefore, he has made more than he needs to give out, so he could be sure that he's made enough. However, remember, these values I've used here for the 250 and the 9,000, they are not the actual correct values for the volumes. Okay, remember the volumes are just somewhere between our error intervals over here. Okay, so therefore, we cannot assume that he's going to be giving out exactly 250 milliliter portions, and we cannot assume he's got exactly 9,000 milliliters of lemonade. So what we have to think about is what value do we want to use for the volume of all the lemonade he made and the volume of the portion size in order to figure out whether he's got enough for everyone. So let's start with our portion size. Well, let's think about the worst case scenario for Bob where he's at risk of not having enough. Well, that's going to be when the portion size is at its greatest. So in place of the 250, I want to use the upper bound for the volume of our portion size, because that will be the scenario where he's giving out the most lemonade. And in terms of our other value, so the volume of the lemonade he's made, so the 9,000 milliliters, well, the worst case scenario would be where he has the least amount possible for the total volume of lemonade. So we want to use the lower bound for the volume of lemonade that he has produced. And using those values are going to help us check whether he has enough lemonade to serve everyone, even in that worst case scenario. So let's substitute those values in. So instead of doing 34 times 250, I'm going to do 34 multiplied by, and we want the upper bound of the portion size. So that is going to be the 255 milliliters over here. And we're going to pop that into the calculator. And that gives us 8,670 milliliters. So that's the most he's possibly going to need to be able to give everyone one portion. And now we're going to compare this value to the lower bound of the volume of lemonade he produced. So that is going to be the value 8,500 milliliters. So I'm going to write 8,500 milliliters. And that is the lowest amount of lemonade he's possibly produced. Now that value is smaller than the 8,670 milliliters he might need. So as a result, Bob cannot be sure that he has enough lemonade for his party. So I can now make a conclusion, which is what you're expected to do. So I can say, therefore, Bob cannot be sure he has enough lemonade to serve everyone at his party. One portion. So we're now going to look at a specific type of exam question you can get for bounds. So let's have a look. So we're told that m is equal to root s over t. So it appears that this is a division calculation. Then we're told s is equal to 3.47, and that is correct to three significant figures. So that's already a hint this is a bounds question because something's been rounded to 3.47. And t is equal to 8.132, and that is correct to four significant figures. So once again, something has been rounded to that value. Then it says by considering bounds, so that's a little bit vague, work out the value of m to a suitable degree of accuracy. Once again, a little bit vague. And it says give a reason for your answer. Okay, so this here is a specific type of thing that you might get asked in an exam. And if you haven't seen a question like this, you're likely going to be confused as to what it's asking you to do exactly. So the idea is the end result involves us finding one specific value for m. And to do that, we have to consider bounds. So we're going to start by trying to find the upper and lower bound of m. So step one is find upper and lower bound for m. So to do that, we have to consider where does m come from? Well, it's the division calculation up here. So what we're going to need is our rules for division when we're considering bounds. So I've got the rules written over here, but before we do that, we have to consider the values that m depends on, so s and t, and find their error intervals. So let's start with s, which is 3.47. Okay, so we got s, and it's 3.47, and that is correct to three significant figures. That's our degree of accuracy. So let's put the 3.47 in the middle of my number line. Then we have to identify the third significant figure, so that's going to be the 7. So we're going to add 1 to that place value to get 3.48, and subtract 1 to get 3.46. Then our midpoints are going to be our bounds. So our upper bound is going to be 3.475, and our lower bound is going to be 3.465, like that. Then we can write out our error interval. So we're going to put s in the middle, upper bound to the right, so the 3.475, lower bound to the left, the 3.465, and then our inequality symbols are going to be as usual for when we're working out the bounds of a specific value. So that's the error interval for s done. Now let's move on to t. So t is equal to 8.132. And that is correct to four significant figures this time. So we'll draw a number line and put 8.132 in the middle. And then the fourth significant figure is the 2. So we add 1 to that place value to get 8.133 and subtract 1 from it to get 8.131. Then our midpoints are going to be our bounds. So let's write them in. So we'd have 8.1325 and 8.1315, like that. So there are upper and lower bounds. So let's just write it out as an error interval. So I'm going to put t in the middle, and then upper bound is 8.1325, lower bound is 8.1315. Okay, and then we're going to stick our inequality symbols in like that, and that is my error interval for t. Now let's think about how we're going to use these to actually answer the question. So we still need to finish this step 1, which is to find the upper and lower bound for m, because we're considering bounds in this question. So remember, m is a division calculation is what we've identified. So let's start with the upper bound of m. So that is going to be equal to, and when we're doing the upper bound for division, it is upper bound divided by lower bound. Okay, so it's going to be the upper bound of the number in my numerator. So the number in my numerator is s. But don't forget, we do have to square root that value once we've identified it. And then for my denominator, we're dividing by the lower bound. So that my denominator is t. So I need the lower bound of t. Okay, so this is equal to, and let's identify which specific values we're going to use. Well, for the upper bound of s, that would be the 3.475. So I'm going to write the square root of 3.475. And in my lower bound, of t is what I need for my denominator. So that's going to be the 8.1315. Then we're going to put this calculation into my calculator. And then that gives me a result of 0.229248. And I'm going to put a dot, dot, dot. Now, in this specific question, what we're going to find is that it will be useful to have a few extra decimal places just to see sort of how the number progresses. Now let's do the lower bound. Okay, so I'm going to write LB and then M. And for our lower bound, it's always going to be the opposites of what we've used here. So it's going to be the square root of the lower bound of S and then the upper bound of T. Okay, so essentially we're using the two values we haven't used yet. Okay, so my lower bound of S was the 3.465. So we need the square root of 3.465. And then the upper bound of T, my denominator, would be the 8.1325. And then we're going to put that calculation into the calculator. And we would get 0.2288903. And I'll just put a dot, dot, dot to indicate the number does keep going. That should be enough digits to help with the question. So we've completed step 1, which is to find the upper and lower bound for M. What we now have to do is this part of the question here. So it says by considering bounds, so we have to consider these two values that we have just identified. We have to work out the value of M, so a specific value of M to a suitable degree of accuracy. So based off these two numbers, what would be a suitable value to represent M? Now, what a lot of people say is, oh, the midpoint, if we add them together and divide by 2. Now, that is a sensible choice. However, it's not what you're expected to do in this type of question. What you need to think about is which number does both our upper and lower bound round to? So say that again. Which number does both our upper and lower bound for M round to? So if we have a look at our two numbers, hopefully you'll notice that they both round to 0.229. So therefore, this would be a sensible value to pick for M if we're picking M to a suitable degree of accuracy. So I would say that M is equal to 0.229. Now, it does say give a reason for your answer. Well, you have to state the degree of accuracy that you've just rounded both of those numbers to, and it should be the same degree of accuracy. So I believe I've rounded those two numbers to 3 significant figures. So I could say M is equal to 0.229 to 3 significant figures. And then I would just clarify that both bounds round to this here. So I'm just going to write both bounds round to this value. Now, I could have said something different instead of 3 significant figures here, because actually, if you'd rounded to 3 decimal places, you would have still got 0.229. So there are a couple of options there. Now, you might be thinking, oh, both numbers also round to 0.2 to 1 decimal place or to 1 significant figure. That is correct. However, we tend to go with the number which is to a greater degree of accuracy. Okay, so 3 significant figures is a greater degree of accuracy than 1 significant figure. So we wouldn't use 0.2. So the 0.229 would be my final answer.